Okay, Assalamu alaikum. Am I audible? Can you hear me? Hello? Am I audible?
Hello?
Okay, yeah. Can you hear me?
Sorry.
Walaikum salam wa rahmatullahi wa barakatuh. Okay. Um, yeah, so I think in the last class we were discussing about double carbon chain nomenclature. Yeah.
Yeah.
Today we will
Sorry, let me get
continue.
my note. 1 second. Yep.
Okay, so finally, to complete this nomenclature, we will discuss another
Mm,
topic, and then we will move to isomers. Or
yeah.
did you study
What's the
isomers in the class? Have you started organic
no,
chemistry?
yeah, we did. Can I have an email to send it to you after class?
Email, yeah. I will message you. Okay, I have WhatsApp you. Okay.
Yeah, received it.
So the final topic on nomenclature is going to be to write down the structure or to sketch the structure when the organic nomenclature is given, right? So sketching
Okay.
organic structure when the name is given, right? Okay, so the vice versa of what we have studied so far. Okay, right. So I am going to give a name now. So 2 chloro, 5 iodo, 5 iodo, 4 nitro, 4 nitro, uh, hexanoic acid, right? Yeah, hexanoic acid. Can you try to write down the structure of this particular organic molecule?
2 chloro, 5 iodide, 4
Did you study this also
hexanoic.
in the class?
Sorry?
Did you study about this in the classes?
No, we haven't.
Okay. So now, first we have to identify the number of carbons. That is going to be our first step, right? So since we have
Yes,
six
yes.
carbon, we are going to write down the carbon chain first, right? So comprising six carbons, 1, 2, 3, 4, 5, and 6. Okay, and we have an oic acid, right? So we have oic acid. So now we will consider this as 1, 2, 3, 4, 5, 6, and you can number it in the other way also. Okay, it doesn't matter. Now in the first we should write down the functional group, right? So this is going to be oic acid, C double bond OH, right? So this is okay, done. Now we have to focus on the substituent groups along with the numbers. In the second carbon we have a chloro, Cl, and in the fifth carbon we have an iodine, iodo, and in the fourth carbon we have a nitro, NO2, right? And
Mm,
finally,
yeah.
for the remaining things, we have to add hydrogen, right? So here we should have H3 because the carbon should have four bonds, right, around it. And here we are having one hydrogen remaining. Here one hydrogen. Here CH2, right? Because around this carbon we have only two bonds, so it will have two hydrogens. And here one hydrogen. That's all. So this is going to be the structure of this one. Okay. Have you understood how to draw this now?
Yeah.
Okay, now I will give you another question. So, 4 bromo, 4 bromo, 2 chloro, 2 chloro, 6 hydroxy, 6 hydroxy, hexane 3 on, hexane 3 on, okay, hexane 3 on. Can you try to sketch this?
Okay, so if I start, I have 6
You can
carbons.
even draw on the screen also. Later we can check it.
Yeah, okay. So I have 6 carbons. So 1, 2, 3, 4, 5, 6 carbons. And then ane means there's only a single bond. But then one means it becomes a ketone, which means you will have a CO bond. So let's write out O there. And then, but that's on the third one. So oops, let me write this out. You write this, it will be the third one. So let's write here. That should be an O actually, but let's see. And then you've got bromo on the fourth one. So we write Br here. You've got 2 chloro, so Cl. 6 hydroxy. 1, 2, 3, 4, 5, 6. Put a hydroxy. That means you have an OH in it, so OH. And then I believe that is it, so just fill the rest up with hydrogen. So that's got
Yeah, that's fine, but here there is a mistake, right? So between this carbon and oxygen, there should be a double bond, right? There should be a double bond, right? And if you have double bond, this hydrogen will not come, right? So this is the structure, right? Is that okay? Right? Between
yeah.
carbon and oxygen, there should be a double bond because we have on as the functional group, right? So carboxyl groups C double bond O, right? So C double bond O here, that is the mistake. And now, yeah, the rest of the things correct. Okay. Now can you try this one?
Yeah. 2 is that okay? So 3. There's 3 twos and then dimethyl. Wait, hold on. Let me see this. 2, 2 dimethyl 4 hydroxy pentanoic acid. Okay. So pent means 5 carbons. So 1, 2, 3, 4, 5. And then if it's an oic acid, you're gonna have a COOH. C. So if you want to draw a COOH, okay, wait, we'll come back to that actually. And then you'll have 2,2 dimethyl. So you've got methyl here, which is CH3. And then hydroxy pentan on the fourth one. 1, 2, 3, 4. Got pentanoic acid. Okay, so pentan. So this will be an OH then, and then you have an oic acid, which will will have a double bond to an O and a one to an OH. Oh no, if I'm going to do on that side then. So I'll have a double bond to an O and then OH. and then the rest get filled up with carbon. So, well, not carbons, hydrogens.
Yes, that's awesome.
Is that right?
That's awesome. Yeah. Okay. So with that, we can conclude this nomenclature and move ahead with the next topic. Okay. So now we can either start the organic reactants, or else we can even start isomerism, right? But
Uh,
yeah, this is going to be your module. I didn't go through your module. Um, yeah, so here you can see, right, the nomenclature,
yeah.
right? The acetone and propanone, yeah, these are the things. What are the products of reactants? Okay, so we have to study the organic reactants, right? The organic reagents
Yeah.
used in organic reactions, okay? And
Is
then,
that just hydration, halogenation,
yeah, everything, yeah, we have to study
halogenation
that,
and stuff?
yeah. And then finally, we have to
I have
perform
done
some,
some,
yeah,
but yeah.
we have to perform some conversions also, right? We have to synthesize organic
Okay.
compounds. And then we have to study the properties of organic acids and bases. What are the properties and uses of polymers? Yeah, polymers also we can study, but we can even study this under industrial chemistry, the final topic. Okay. Then yeah, this is very simple, right? But now I am going to go with the Sri Lankan curriculum, right? So that you can get a complete understanding about the organic chemistry. But this is very simple, right? If you consider what we have studied in organic chemistry, they have just included a small point. But
Yeah.
if you study further, then you can get a complete understanding, right? So let's come from here, right? Is that okay to you?
Yeah.
Okay, okay. Because when we have extra knowledge, we can easily go to the answers as well for your exams. Okay, so we should be very clear about theory. Now, here this is the table of contents. We have completed all these, right? So the classification of organic compounds, alcohol, the structure of these types of organic compounds, and IUPAC nomenclature we have done. Now we will come to this isomerism. After that, in the last class, I remember you were suggesting to teach me something. Can you recall it?
Yeah, can you do the bromine water test? Because I didn't understand that when we did it in class.
Bromine water, right? So when we study organic reagents, we can study under that, right? So in our list, it is there, the bromine water. So if you have a double bond or triple bond, you can react, or you can administer a halogen, right? So in that case, for
Yeah.
example, this is very simple, right? So if you have C double bond C or C triple bond C, right? So unsaturated things. So what will happen if, okay, for example, there is a compound, if you could Br2, so it will become CCBr, and if it is C triple bond C, it will become CCBr, right? So Br will be added. So we have types of chemical reaction. We have to study, we have to come from the beginning. We have to study the types of chemical reaction: nucleophilic addition, nucleophilic substitution, electrophilic addition, electrophilic substitution. Did you study all these things?
Not everything, but I have done. Oh, let me just quickly tell you what I have done. I have done hydrohalogenation,
Okay.
halogenation.
Halogen. Okay. So halogenation means
Oh, yeah,
we are
found it.
going to add halogen, right? So halogen means Cl2, Br2, I2. So we should have these as the substrates, right? So these are called substrates. You know substrates? Yeah. So substrate simply means the substances we are starting the synthesis with, right? So very simple, very simple. Nothing to worry. We can study everything,
Yeah.
right? So okay. So now we will go to the isomerism, right? We will come from
Okay.
here so that we can go in an order, right? So we don't want to study here and there. We can go in an order. and we can complete the entire module. Then you can have a complete understanding about organic chemistry. Yes. Okay, so this is going to be isomerism, right? So the new topic, right? Isomerism. So isomerism means for a particular molecular formula, we will have different structures. This is the idea. The simple idea is what? For a particular molecular formula, for example, the chemical formula is the same, but they have different structures, right? Can you read it? Isomerism is the existence of different compounds. Different compounds. Different compounds mean the structures are different, right? Structures are different that have the same molecular formula. Same molecular formula means the number of atoms present in the molecule are same. The number of
same.
Okay, same. Different compounds having the same molecular formula are called isomers, right? So such molecules are called isomers. Isomers can be subdivided into constitutional isomers and stereoisomers, right? So isomers, we can two categories: constitutional isomers and stereoisomers. So constitutional isomers, in the sense, only the what do you call this? The order, right? So we have three types under constitutional isomers, right? Chain isomer, functional group isomers, and position isomers, right? So these are the three categories. And under stereoisomers, we have enantiomers and diastereomers, right? So this is going to be the summary of what we are going to study now. So isomers, we have constitutional isomers and stereoisomers. Under constitutional isomers, constitutional means what? So first we will try to understand the term, right? Constitutional. In English, what's the meaning of the word constitutional? Give me a sec. Okay, so sorry. So here constitutional means it's related to the structure, right? So the chain will change the position, right? So simply constitutional means what do you mean? I don't know if it has the direct meaning with structure, right? So the structure is going to be changing, right? So the structure of the isomers or the compounds will be changing, right? So if it has a different chain, right? So it might be a linear or a branched, right? So it can be chain isomers mean the linear, there is no branch, and branched one. And position means the position of the functional groups may be different, the positions, right? So the functional group may be in the first carbon or second carbon, right? So the position of the functional group is going to change. And functional group isomers means the functional group itself will change, right? For example, for a particular molecule, here we have oic acid as the functional group, but if it becomes alcohol, then again the functional group changes, right? So we will discuss some examples for each type, right? And stereoisomers mean this is enantiomers, diastereomers, right? So these are the two categories, right? So you will study about these two things even in A-level syllabus in Sri Lanka. We don't have any much detail about these stereoisomers, but I don't know, let's see, right? So whatever we have, we will study. Okay, right. Now here you have understood what we are going to study now, right? So this is going to be your chart, what we are going to study in today's class. Okay, right. So let's come from here. Where's that? Okay, so constitutional means structural, right? What's the meaning of constitutional in English? Constitutional means
structure.
Yeah, it's what is constitution mean? It is the the written rule of country or something like that, right? I don't know, constitution of a country.
Yeah.
Okay, so a kind of thing, right? So that structure of how the country should be ruled, right? It's a kind of thing, right? So constitutional means structural isomerism, right? So isomers that differ from order in which the constituent, right? So constituent atoms are connected, right? Constituent means what? The components or the parts of the parts, right? Constituent. Yes.
Sorry, you're breaking up. Can you repeat that?
I'm sorry? You can't hear me?
No?
Yeah.
You're No, you were breaking up a lot. I think it's just my Wi-Fi's a little bad. Can you repeat that last bit?
Okay. So here the constitutional means structural, right? So it's related to the structure
Yeah.
or the appearance, right? So
Yeah.
constituent atoms mean the atoms by which the molecule is made up of, right? So constituent means simply parts or the components, right? Connected to each other are called constitutional isomers, right? Hence they have different structural formulae. A few examples of constitutional isomers are shown below. So here you can see for the same molecular formula, we have different structures, right? So this is a structure, this is a structure, this is a structure, right? So different structures. So these are called constitutional isomers. And here for the same structure, you can observe that here the structures are different. Three structures are different. Here for the third molecule also we have different structures, right? So these are called structural isomers. Now you should have an idea about what these structural or constitutional isomers are, right? Can you read it? This one.
Yeah. Constitutional isomers are generally subdivided into chain isomers, position isomers, and functional group isomers.
So these are the
These
three
subdivisions
categories,
are not
right?
exclusive and can overlap.
Okay, so these subdivisions are not exclusive or can overlap. So sometimes, what does it mean is, what it means is, sometimes for a particular molecular formula, we may have both chain isomers and position isomers. So they are not exclusive, right? So exclusive means what? Mutually exclusive sets.
Only for one?
Yeah, in mathematics, mutually exclusive
Only
means
for
there
one.
is no intersection, right? So they can overlap. They can overlap means, so for a particular molecular formula, we may have both chain isomers and position isomers, right? So here you can see there is an overlap. This portion is overlap, right? Overlap. So these two sets are mutually exclusive, right? Mutually exclusive. Have you understood that? So yeah, okay. Right, now chain isomers.
Yeah.
Okay, so chain isomers mean they are the, okay, so you should know the chain isomers mean the chain is going to be different, the chain, right? So sometimes it might be a branch or linear one. So if you look at this one, here the same functional group, OH, here also OH, here also OH. But here this is going to be your chain, here this is going to be your chain. The chain is different, right? Here there is no branch, but here there is a branch. And here this is going to be a chain. Again, the chain is different, right? So chain isomers are those who have different hydrocarbon chains for the same molecular formula. So when the word isomers come, we should include the same molecular formula, and for chain you should mention that different hydrocarbon chains. That's all. Okay. Now position isomers. Position isomers mean the position isomers are those who have, as I mentioned you, the same functional group. There will be same functional group, but the position of the the number of carbon on which the position on which the functional group falls will be different, right? That's the only thing, right? So here you can see OH, here also OH, here also, here, yeah, if you consider these two, right? So this is 1 propanol and this is 2 propanol, right? So if the name changes, they are different, right? They are different. So position, only the position changes. That's why we have mentioned this is 1 propanol and this is 2 propanol, because the functional group is on the second carbon here in the second structure. That's all. Okay. And here if you look at this one also, CH3, CH2, C triple bond CH. So here the functional group is triple bond. So ine, butane. So it is the triple bond is in the first carbon. Here it is in the second carbon, right? So these are called positional isomers or position isomers, right? Okay. And functional group isomers means, that is very simple. Here you can see the functional groups are going to change, right? So here now if you look at this one, here this is going to be the formula, but here if you, for this structure, the functional group is OH, but here this is ether, right? This is ether. Yeah. Okay, so the functional groups are different for a same particular, for the same what do you call this, molecular formula. Okay, and here also the same thing is happening. This is same, but here on. Oh, see here al, here on, here al, here on. So they are different. Okay. So examples of functional group isomers. Here chain isomers, position isomers, and functional group isomers can overlap. That is very important, right? So if you want, you can highlight that, because for a particular can overlap mean isomers can overlap mean for a particular functional, what do you call this, molecular formula, we may have both functional group isomers and chain anything, right? It can overlap among themselves, right? They can overlap among themselves, right? Okay, so here constitutional isomers for the molecular formula C4H8O. So all these structure represent the same molecular formula. Now we will compare pairwise and identify which constitutional isomers they belong to, right? So if you, now I will name them, right, for your practice. This is 1, this is 2, this is 3, this is 4, 5, 6, 7, 8, 9, 10, 11. We have 11 structures for the same molecular formula. Now if you compare 1 and 2, so can you name the constitutional isomers they have among themselves? Between 1 and 2. 1, 2. Right. So what's that? Here I will do this for you now, right? So CHO. So there is no functional group isomers, right? Functional group isomers is not there. But the carbon chain is different. The carbon chain
Hello?
Yeah, I'm sorry, I was disconnected. Am I audible now?
Okay. Yeah.
Okay. Let me. Okay. So between the structure 1 and 2, can you identify the constitutional isomers they share among themselves between the two? Yeah. Go ahead. So here functional group is the same, right? Functional group is the same, but the only thing is the chain is different. So this is going to be chain isomers. Chain isomers. They are chain isomers. And the position, the functional group in both structures, they are in the first carbon. So that is not a position isomers also. And between the second one and third one, between the second one and third one,
between the second and third one, they're different functional groups. So it is going to be a functional group isomer.
Functional group isomers. Okay. And what about the carbon chain? Here 1, 2, 3. Here 1, 2, 1, 2, 1, 2, 3, right? And here 1, 2, 3, 4. So here you can see the carbon chain also differs. The carbon chains also differ, because here we have 3 carbons, here we have 4 carbons. So in addition to functional group, the second and third share the chain isomer as well. Yeah, chain isomer as well. Is that clear now? Is that clear? Yeah. If you go back to your chain isomers, here you can see the chains are different. Right? So similarly for the second and third. Now can you compare the 5th and 11th? Yeah, you can. Yeah, you can have a lot of combinations, right? So 5 and 11. Let's compare 5 and 11.
5 and 11. Okay. So your carbon chain is 1, 2, 3, 4. Okay, and then on this one you've got 1, 2, 3, 4. So it's the same carbon chain, the functional group. You have a. Ooh, no, you don't. You have the same functional group. What's the? I forgot what the third one is. Functional group, chain, and what's the third one?
Position, right? Position. Now you can see here
Position.
between 5 and
Discipline.
yeah, what's the difference? You can see that, right?
Position.
Yeah, position is changing, right? Because the functional group is
Yeah.
on the second carbon here in the 11th one, and here it is in the first carbon. So this is going to be position isomers. Very simple. Okay. And now we will move to the stereoisomers. Now you can just read it, right? So stereoisomers is the existence of compounds whose structures differ from each other only in the orientation of the bond, right? So here we should have double bond carbon, and we have EZ combination and all, right? Yeah. I don't know. Yeah, you can see here double bond carbon, and I don't know if it is included in your syllabus. Cis trans. Did you study these things? Okay, anyways, we'll study this one also. Okay.
No.
So, yeah, okay, it doesn't matter, right? So, stereoisomerism is the existence of compounds whose structures differ from each other only in the orientation, right? So, here in the orientation, in the aspect of orientation of bonds, right? So, orientation of bonds mean there should be a carbon-carbon double bond, and cis means we will be having something like this, right? So, C double bond C. Here we should have A, B, C, and D, right? So this is going to be a stereoisomerism, right? So the orientation of the bonds, right? So if it is A and D are same, if they are in the cross, in this trans position, we will call trans. And if they are in the same orientation, we will call it as cis trans, right? So these are the two things. Okay. So space. Stereoisomers have the same structural formulae. They have the same connectivity. So these are the just properties, right? So their constituent atoms are connected in the same order but different in the manner in which atoms group, right? So they cannot be superimposed. Superimposed means what? For example, superimposed means, for example, if you keep your if you keep your hand on your on a mirror, the image and your real hand are superimpossible or not? Superimpossible means can they overlap? Here, if I want to explain this here. Wait, I can visually explain, right? Give me a sec. For example, let's say you have a mirror, right? You have a mirror, and okay, so you have a symmetrical object. And the image and the symmetrical object are superimposable, right? So if you bring the image and the object together, they will overlap. So they are called superimposable images. But if the object is asymmetric, then they are not superimposable. They cannot overlap, right? If you have if you have a hand, right? So let's say you have your hand and your image of your hand, and if you bring them closer, your thumb will overlap with the small finger only. Your thumb of the real image, or your can you imagine that your thumb is there with the image of your hand, the thumb will overlap with the small finger. Yeah, so they are not superimposable. Have you understood that? The meaning of superimposable? I'm unable to download the image.
Yeah.
Yeah, now you can see, therefore their structures cannot be superimposed on each other even though they have the same molecular and structural formula, right? Now if you look at this one here, they might have explained it, right? Yeah, now if you bring this here, right, if you bring this here, if you bring them together, now they are superimposable. Why? Because this chlorine will overlap with this chlorine, and oh yeah, they are not superimposable. Why? Because this chlorine can overlap with this chlorine if you bring them together, right? This fluorine will not overlap with this fluorine, right? Because there is there is no uh, equal distance between them. But this bromine will overlap with this bromine, and this hydrogen will overlap with this hydrogen. But will this fluorine overlap with this fluorine? Have you? I don't know. How can I explain this?
Yes.
For example, okay, you have an object like this, right? You have, okay, let's consider this as our hand, right? So if you bring your hand, now for example, let's say this is going to be our thumb, and this is kind of small finger, right? I don't know. How can I read? Like for example, this is your mirror, right? This is going to be a thumb, and you have folded your other fingers, right? So let's consider that like this. Okay, and what will be your image? This is how it will appear, right? I'm roughly sketching it. Okay, right. So this is your hand.
Yeah.
This is your mirror, and this is going to be an image. Now tell me, superimposable means what? Have you heard this term superimposable anywhere in physics or somewhere? Are you familiar with the term superimposable? Superimposable means they can perfectly align, or they can perfectly overlap. They can perfectly overlap, right? I don't know if you can understand this or not.
Hello?
Yeah, okay. Am I audible now?
Yeah.
So we are talking about superimposable nature, right? So have you already heard about the word superimposable anywhere? Superimposable. Hello, am I audible? Okay, so yeah, so we were talking about the superimposable nature of objects, right? So have you already heard about the superimposable nature anywhere? So for example, superimposable
No.
nature means simply two objects can overlap, right? So if you now you can just experiment it, right? Um, you have folded your other fingers except your thumb, and if you keep in an image in front of an image, so this is going to be your image, right? So this is going to be an image. Now if you bring them together, are these two superimposable or not? Can these two figures overlap each
Yes.
other? Can these two figures overlap each other? Now we are bringing them
Yes.
together, right? Now I'm just shifting this hand here. Are they superimposable?
I believe so.
Can they overlap?
Oh, wait, you mean just shift it and you can't flip it?
Yeah, no
Without
flipping, no
flipping it?
flipping. Well, without flipping.
Oh, then no.
Then no,
Then
right?
no.
So this is called not sup. Okay. So this is going to be called as not superimposable, right? Not superimposable. So similarly, here if you look at this structure, right? This structure, this is this superimposable or not? Can you check it? So yeah, so this chlorine and this chlorine, can they overlap each other? If you bring this here, this bromine and this bromine can overlap, but this
Yeah.
chlorine or fluorine cannot overlap, right? So if you have to have
Yeah.
some imaginary power also, right? So they are not superimposable. So they are called stereoisomers, right? So they are called stereoisomers, right?
Yeah. Okay.
Right. So understand. Yeah. So under stereoisomers, we have two things, right? So first one is going to be
Yeah.
cis trans. So they are coming under diastereomers, right? So diastereomers are nothing but we can even call it as geometric isomers. Geometric isomers mean we should have some properties, right? So between two carbon atom, we should have a pi bond. We should have a pi bond. And the second
Pi bond.
condition is there should be a spontaneous electron revolution. So we call these are just terminologies, right? And the next thing is there shouldn't be the same system on the carbon atom, on the same carbon atom. Here, if you have A, here we cannot have A. The same carbon atom should be in the next or adjacent carbon atom. Right? So now simply I can explain. Yeah, if you look at this picture, now this is going to be diastereomers, right? Because it has carbon-carbon double bond, and this A, this B, this P, and this Q, right? So here you can see they are different. Now here also they are different. A, B, P, Q, they are different. But if we have something like this, carbon-carbon, here A, here also A, here P, here Q. So this cannot be a diastereomers. This cannot be a diastereomers, right? And these diastereomers are also not superimposable, right? So if you have cis and trans counterparts, if you bring them together, they cannot overlap each other, right? That's the condition. That's the condition. Is that okay?
Okay.
Right.
Yeah.
Now you can read it for your understanding. So geometric isomers is one occasion where diastereomers is seen. Diastereomerism is seen, right? So diastereomerism is a concept in organic chemistry. A carbon-carbon double bond consists of a sigma bond and pi bond. That's obvious, right? Due to the pi bond, the two carbon atoms cannot freely rotate, right? Now, okay, so now I told you that the carbon-carbon atom shouldn't spontaneously revolve, right? Because if you have carbon-carbon single bond, these two carbons can revolve around this bond, yeah, because only one. For example, what can I tell? You have only one pen, right? So you have a pen, and you have two books, right? So you have two books. This is two book. There are two books, and you fix these two books with the pen. I'm just telling you this example, right? And can you rotate these two books around this pen? Can you freely rotate these two books around the pen?
No.
Yes or no?
No.
Why? Now you see the pen should be kept stationary, and yeah, now there is an axle, right? There is an axle, and around the axle you can rotate the books. Let's consider, right? So
Okay.
we have fixed it, and can we rotate these two books? Can I rotate these books? Yeah, we can rotate, right? For example.
Yeah.
Okay, for example, let me show it to you. Here you can see, right? I
Yeah.
have, okay, so let's say this is one object, right? So I have this pen, and this is one pen, and I have my phone here, right? So can I rotate my phone? Yeah, I can be
Yes.
able to rotate my phone, and I can rotate this one also. Yeah, I can rotate this one also.
Yeah.
But if I have two pens, and I have fixed two pens here, you can see I have two pens, right? I connect my phone with these two pens. Now can I rotate this phone around one pen? Is it possible?
No, because the other one will fall.
No. Why? Because the other pen will not allow the phone to rotate. Can you understand? Yeah. So if we have a pi bond and a sigma bond, the carbon atoms are not freely movable or freely rotatable, right? Freely rotatable. So
Yeah.
okay. So we will go to the note now. Give me a sec. Okay, so you can read here, due to the pi bond. Now if there is a sigma bond only, the carbon atoms are movable or rotatable, right? Freely rotatable. But due to the pi bond, the two carbon atoms cannot freely rotate about the sigma bond, right? As I mentioned, let's say my digital pen is the sigma bond and the normal pen is the pi bond. So my phone cannot be rotated around the digital pen because the normal pen will not allow it to do so. Is that clear? Am I audible?
Yeah.
Okay.
Yeah.
Okay. So both alkene carbon atoms and our four atoms attached to them are all in one plane. For geometrical isomers to exist, these things you can read and understand, right? So you have got the idea, right? Now we will talk about cis and trans nomenclature. So cis and, okay, I already told you there will be cis and trans also in our nomenclature, right? So cis means, now you see here there should be a diastereomerism. That diastereomerism may be cis or trans. So cis means the orientation should be in the same, the same orientation. Trans mean this one. For example, let's say you can read it, right? So in alkenes,
Yeah.
because diastereomerism can be discussed in alkenes only. There should be a carbon-carbon double bond. Are used to indicate the geometrical relationship. The geometrical mean, what is geometry? That's just a branch of mathematics, right? So we are going to study
Yeah.
the structure of shapes, right? That's all. In two groups attached to different carbon atoms in the same double bond. Consider a plane passing through carbon-carbon double bond, which is perpendicular to the plane of the molecules, right? So the simple idea, right? For example, carbon-carbon double bond is there. Now, if you have A, here also A, here we should have B, and here we should have C. Now, the similar system, what are the similar system here? A and A. These A are in the cross-sectional way, or in the transposition, right? So against each other. So this is called trans isomerism. This is what? Trans. And for cis, the idea is very simple. Let's say the same carbon. Here we have A, here we have A, here we have B, and here we have C. Now, if you look at the same system, A and A, they are in the same side or same orientation, right? So here, since they are in the same orientation, this is called cis. Cis. And here they are in the opposite to each other. So this is called trans. This is the idea. Is that clear now? For example, if we have C, double bond C, here we have H, here we have H, here we have CH3, and here we have Br. So when we name it, we will denote that this is going to be a trans structure, right? Trans structure. And if you have the same molecule, but here in this structure, C double bond C, here H, and CH3 is here, and Br is here. Now you can see the orientation of the arrangements of the molecule is different in the both structures. So that's why they are called stereoisomerism. Is that clear now? Now, how do you call this? Since these H and H, the similar structure, are in the same side, this is going to be a cis structure. Cis. Is that clear now? Is that okay? Now you can see here, this is trans. Now when we name this one, we have to mention the, that is not actually necessary, but for a perfect nomenclature, we have to mention the stereoisomerism also. That's why we are studying it, right? Okay. So if you name this 2-butene, that is also okay. But if you want to consider the stereoisomerism also, we have to mention the position or the arrangement, whether it's trans or cis. Okay.
Okay.
So cis and trans nomenclature. This is the idea. Now enantiomers mean, this is going to be enantiomers, right? Enantiomers mean the mirror images, right? So diastereomers are the geometrical arrangement. Here enantiomers are the mirror images, right? So isomers, which are mirror images of each other, are known as enantiomers. Definitely, right? So here this structure and this structure are completely different. Are they same? Now, just like our image of our hand and our image, if it is our right hand, then the image will be definitely the left hand, right?
Yeah.
So how do you call that property in physics? We have a name. In light, did you study? There is what do you call this? Because in the images of objects are I think side reversal, right? The side reversal. There is a name. What's the name? Do you remember? Did you study light? I don't know. Now there are properties of the images appearing on the mirrors, right? What's that? It's not coming. Do you remember? Did you study this physics? I mean, the light concept.
No.
Wait, there is a property. What do you call it? Okay, leave it. Okay. So here you can see this one, this structure and this structure are different, but this is the mirror image of this one, but they are both enantiomers, right? Because they can be rotated along the plane, right? So you can see here the definition, right? So isomers which are mirror images of each other are known enantiomers, right? So let's say we have one particular one particular molecule, and the mirror image of that one is there, but they are not superimposable. If they are superimposable, they are not enantiomers because they are similar structures. If they are not superimposable only, they are different, and we can give different names. That's why we call them as stereoisomers, and under that we have enantiomers, right? Have you understood that now? Now here, these now you can see here, these cis and trans structures are also not superimposable, right? So if you have this and this, definitely this and this are different, even though they have the same chemical formula. Their structure or the appearance or the arrangement of the atoms in the molecules are different, so they are completely different because the name is going to change, right? Because here we call it as cis-2-butene, and here this is going to be trans-2-butene, so the name is different completely. Yeah. So similarly, if you have a carbon, and the carbon should comprise four different groups, and they are mirror image of each other which are not superimposable, then they are called enantiomers. Is that clear? Can you repeat what I just said now?
Not really. I got very confused.
So yeah. Can you read it? Can you take some time and read it?
Okay.
Yeah, you read it and explain what enantiomers are.
So yeah. Okay, so 4 different groups have all making
My laptop has been inverted by arms.
Okay.
Yeah, what's that?
Yeah, I think I somewhat get it.
I'm sorry?
I think I somewhat understand it.
I can't hear you. What's happening? Yeah?
I think I, to a certain extent, understand it now.
Okay. Can you explain me what you have understood?
So it's like the enantiomerism is where you have your isomer, and the main part of it is that it is symmetrical, and what's it called? It has 4 different groups attached to it, and that that when you have the light pass. Okay, I'm not sure about the light part. That's
because
one bit which I'm not 100%
so they are
sure.
optically active compounds. Mean what do you call this? Because it will change the light, the light in the opposite direction, right? So I cannot explain it in words. You should experimentally perform it, right? Anyways, you can see this. As the enantiomers rotate the plane of polarization, they are also known as optical isomers, because the name is optical isomers. The name why we give these optical isomers is when we strike the light, right? So the light will be reflected in the opposite directions. Okay, so compounds which rotate the plane of polarized light are known as optically active component. You don't want to worry about that now, right? So you can see here stereoisomers which are not mirror image of each other are known as simply stereoisomers which are not mirror images of each other are known as diastereomers. Now, that is the opposite of enantiomers. Enantiomers are the mirror image. If they are mirror image, then they are called enantiomers. And if they are not mirror images, then they are called diastereomers, right? Therefore, geometrical isomers are not mirror images, right? We have already discussed. Now we have studied stereoisomers, right? So under stereoisomers, what did we study? Can you recall? Under stereoisomers,
Sorry?
we have studied about enantiomers and diastereomers, right? So enantiomers are the geometrical isomers. There should be carbon-carbon double bond. There should be a single bond and a double bond. And under that we have cis and trans. Cis means what? The same system should be in the same side. And trans means they should be in the opposite directions. And under diastereomers, we studied. Under diastereomers, we study. So this is about diastereomers. In enantiomers, we studied about mirror images. There should be a carbon. There should be a single carbon. Around the single carbon, we should have an unsymmetric different groups. The different groups should possess, right? The carbon should possess 4 different groups, and they are the mirror image of each other. They are the mirror image of each other, but they are not superimposable. They are not superimposable mean they cannot overlap. So let's say, now for example, if I can explain. Now can you check if this is diastereomers or not, right? Carbon, CH3, Cl, Br. Is this a diastereomer structure?
Sorry?
Is this a diastereomer structure?
No.
Why?
Because it's different. Like the chlorine and bromine have to be the same.
No, not actually. That's the reason. Because the reason is here the same groups come in the same carbon, but they should be in the adjacent carbon. But if I draw this like this, carbon, CH3 is here, but this carbon cannot again have CH3. It should be a different one. So let's say this is Br, and here this carbon can again take CH3, and if this carbon takes CH3, the same carbon cannot take CH3 again. It should be something else. So let's say Cl. Now is this a diastereomer? Is this a diastereomer? Is this confusing?
No.
Is this a diastereomer? Now this is the summary, right? So we have studied about, I don't know. This is a bit confusing chapter, but if you can understand this, then that is nothing, because organic chemistry may be difficult only for this reason, right? Now we have studied this constitutional isomers. You don't have any issues, right? So under stereoisomers, we have enantiomers and diastereomers. So enantiomers are the geometrical isomers, and diastereomers are the geometrical isomers, and enantiomers are the mirror images. Enantiomers are the mirror images. So mirror images mean there should be an unsymmetrical or non-overlapping mirror images. Have you understood that? Now which means here if you have carbon, here it should be A, it should be B, it should be C, and it should be D. So if you take the image of this one, and the image and the object are not superimposable, they cannot overlap each other, then they are called mirror images, enantiomers. And diastereomers are geometrical one, which means they should have sigma bond and pi bond, and what's that? So here, this is what I wanted to tell you, right? Here, yes. Now here you can see carbon-carbon double bond is there. Here CH3, here CH3. So they are in the same direction. So they are diastereomers, and the type is cis-trans. This is not diastereomer, right? Why? What's the reason? Because the same system comes in the same carbon, so it cannot act as a diastereomer. Here they are diastereomers and they are cis because in the same direction. And what about this one? This is the summary, right? Can you figure them out? Carbon double bond is there, and here CH3 is here, and CH3 is here opposite to each other, and here Br and here Cl. Now so if you consider this carbon, the groups attached to this carbon are different, and here the same, but the same system is in the opposite direction. So they are diastereomers and trans. Is that okay now? Here in this?
Yeah.
Yeah. Okay. Now we will move to the hydrocarbons and halohydrocarbons. Even, yeah, if it is difficult, you can skip that. And if you study this in the class only, we have to study again. If you don't understand, and you better ask about this from your teachers if you want to study anything, because in A level, if you compare, if you consider, let me show you the A level papers. Now can you see this? So here we will be having 50 MCQs. This is the structure of Sri Lankan curriculum, right? So way harder than
Yeah.
your curriculum. So you have only 20 MCQs, right? In the final exam? Only 20 MCQs. How many MCQs do you have in your final exam?
I believe it's 15.
15 or 50?
Yeah. 15, and then it's, I think, about four. Was it 40? No, it was, I think, 60 short response, and then the remaining marks will be long response.
Yeah, now there will be 50 MCQs and there will be 4 structured essay questions, and we are supposed to write 6 essay type questions also, right? And yeah, now you can see here there will be a huge question on isomerism. We have to find out the structures, but as far as I gone through your past papers, that's very simple, right?
Yeah.
If you can study all these things, and even definitely if you go to university, I just heard you want to become you want to enter medical faculty. Is that okay?
Yeah.
That's fine. And then if you go to university, definitely chemistry will be needed, but I don't really understand why you don't study biology for becoming a doctor. Okay, now can you try to answer this fifth one, this one?
The fifth one, okay, the IUPAC name of the given compound is, okay. So it will be there's a O, so it's none of these. So it's either 1, 2, or 3, and then we'll go 1. Oh, there's an O here. But then there's also own. So the own gets rid of this, so it'll be hydroxy something own, and then your longest carbon chain is 1, 2, 3, 4, 5. So it'll be pent. All of them are pent, and then the only difference is afterwards. Then is it will be the numbering. Okay, wait. A B C D F G H. So it will either be 2 or 3, and then 1 bromo or 5 bromo. Is it number 3?
Number 3, let's check. I don't know. So here, yeah, so we have to use elimination technique, right? So here 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. If you consider this direction, this is going to be on, is going to be our functional group. So I can eliminate 4th and 5th, right? So on. And if you name it the above one and below one, here 1 plus 2 plus 5, and below one 5 plus 4 plus 1. So the least one is going to be what? This one. So they will consider above one, right? So 1
Yeah.
1 hydroxy.
So it'll be 2 then. Yeah.
1 hydroxy, 5 bromo. Yeah, so the answer is going to be 2. You said 3, right? So you have to be very careful, right? You have to be very careful while naming. Is that clear? Can you check if the answer is correct? Can you try to
5
complete?
here, 1 hydroxy,
And 2 methyl pentene, yeah? Okay.
and 4, yeah.
And here you have to be very careful. You have to take the sum of the carbon atoms on which the substituent groups are there. Yeah. And then we will have an essay question under organic chemistry. You can see this. We'll try to answer all these questions also if we have time. Okay. For that we have to understand the entire theory, because chemistry is the same everywhere, but the only way of teaching or the conditions or the things are different, right? Okay. In my A-level times, we have to spend 15 minutes for this essay type question, right? And if you make a single mistake here, then the exam is going to flop, right? And because I really enjoyed organic chemistry in A-level time, right? And then I took chemistry as a subject in the university also. Last semester, I had a backlog in organic chemistry, okay, because I didn't have time to study that one. But that was a really easy subject. It was a kind of difficult. That's why I dropped chemistry and then I went for statistics specialization. Okay, so now we will have to do this. This one you can see here. This conversion should be done, and we have to write down mechanisms and everything. Yeah, I don't know. I as far as I looked at your past paper, you are not going to study that much deeper. But I will teach you, right? Because even in the university it might be helpful. Okay. Here we have to perform. Now we have to synthesize chemical substances, organic chemical substances, right? That's what we are going to study. And that's the purpose of organic chemistry. Ultimately, you have to synthesize a new organic molecule, yeah, using the raw material or substrates. We call the raw materials as substrates, right? And there might be, these are called intermediate products, and this is going to be our final product. So now there are some term words, right? So we are now, this is a synthesis, right? So this is just a procedure for synthesizing cake. So we start with this substrate. This is going to be substrate, and this G and this structure are intermediate products, and finally we have the products. And we are going to study lithium aluminum hydroxide. Did you study this lithium aluminum hydroxide? And did you study pyridinium chlorochromate, PCC? These chemical reagents. This is what we are going to study. The roles of each chemical reagents used in chemical reactions, organic chemical reactions, right? We are going to study about each and every thing, right? And then we can come to these things. With this idea, we'll now move ahead with this. Okay, now is that clear to you now? Now we will go ahead with hydrocarbons and halohydrocarbons, right? So did we study this already? I have annotated. Before that, we have to study about benzene also, but benzene we can come later. Now let me introduce some chemical reagents, right, so that you can have an understanding. Okay, now let's do it. Let's do like this, right? I am going to teach you some popular or famous organic reagents, right? So some famous organic reagents. Later we will come here. Okay, so let me add a new page, and you can simply put the heading organic reagents used in organic reactions, right? So now let's put up a list, right, that we are going to study. First of all, we have to study about tolerance reagent. What's that? Did you study about tolerance reagents?
No.
Tolerance reagent, right? The first thing. And the second one is going to be NH3CuCl2, ammonia CuCl2, NH3 slash CuCl2, right? So these two and these three are supposed to be subscript, right? Yeah. Let's study little by little, and these are very important. Because I have my note in Tamil medium, this is okay. So I'm going to just translate and teach you, right? So then we have to study about feelings solution. Have you studied about feelings solution?
No.
You don't take biology, right? Oh, feelings solution. Okay. And then we have to study about Lucas reagent, right? Yeah, Lucas reagent. Okay, Lucas reagent. This is particularly used for alcohols, right? And then we have to study about oxidation tools, oxidation reagents, right? Oxidation. Yeah, then we have to study about oxidizing tools and reducing tools or reducing reagents, right? Reducing tools. Okay, and then we have to study about the eighth one, lithium. Yeah, that is coming under that. And hydration tools. Now, hydration tools mean we are going to add water to the organic compounds. Hydration tools. Okay, and then we have to study about halogenation, right? You study about halogenation.
Yes.
Okay, so we will study about halogenation as well. And then finally yeah, that's then after that we have sodium amide. Yeah, sodium and sodium amide, NaONaNH2, right? NaNH2. So the function of this reagent, because they are very famous. Okay, and then there are a lot of things I'm just giving you. After that we have to perform some conversions using them, and then HNO2. Oh yeah, HNO2 is also very important. HNO2. And then Grignard. Finally, Grignard, right? Grignard. Did you study about Grignard? Grignard
No.
reagent. Okay. Right. So, okay. So this is going to be our syllabus now, right? We have to study all of them. Now we will say Bismillah and start this tolerance reagent, right? Okay. Yeah. So first of all, we are going to talk about the tolerance reagent, right? So you can put the heading tolerance reagent, the first one, right? Okay. So first one, tolerance reagent, right? So if you want to have the tolerance reagent, we can write this in two ways. So ammonia AgNO3, what's that? Ammonia AgNO3, or the second method of writing this one is AgNH3 twice. This is going to be a complex solution. Ag, because when Ag plus reacts with ammonia, it will produce a complex. You studied in inorganic chemistry. Because I didn't teach you inorganic chemistry.
Yeah.
Last year, did you study inorganic chemistry? NH3
A little bit.
Yeah, it will produce a complex NH3 twice plus, right? Because we are going to now, for example, we have a substrate, right? The substrate should have a triple bond or an ul, right? The substrate should combine a triple bond or an ul. And if you put ammonia and AgNO3 together, first it will form this complex, and the complex will react with the substrate to produce a certain product. That's what we are going to study, right? So the first thing you should know about the writing methodology of this tolerance reagent, okay? And the second one is the tolerance reagent may undergo two types of reaction, right? So now the second point is tolerance reagent may undergo two types of reactions. The first one is going to be acid-base reaction. Acid-base reaction. And the second one is going to be redox reaction. You know, reduction and oxidation. Redox reaction. Right? Redox reaction. Now first let's discuss this acid-base reaction. If tolerance reagent want to make a acid-base reaction, this is going to be a substituent reaction. Simply the hydrogen, right? So for example, if you have C triple bond CH, the acidity of this hydrogen is high. So this is going to be an acid, and this H is going to be replaced by this will now this is an acid, right? Because this is a leaving group. This is a better leaving group. We will study about this leaving group and all later because of the electron repulsion happening inside the molecule. This H can release. So it can leave as H plus. So this substance releases H plus. So is this an acid or base? Now the concept is the same. If something releases H plus, that's going to be acid. Yeah? Okay.
Yeah.
So now if you have a this structure, right? If you want to have acid-base reaction between tolerance reagent, we should have this structure C triple bond CH, right? So here this is very acidic because it can quickly release this H plus. And if you put ammonia AgNO3, now it will produce a white color precipitate. And the structure of the white color precipitate will be, now you see here, if this H plus releases and this Ag plus will come and join here. That okay? Because it have to be replaced. Now this is called substituent reaction because the H is substituted by Ag, right? So here let me write clearly and neatly so that you can take screenshot or something. Yeah. Right. First thing you have to know is the writing methodology, and then you have to study the types of reaction that the tolerance reagent may encounter. Right. So acid-base reaction. Under acid-base reaction, we should have this system C triple bond CH. And if you add ammonia AgNO3, it will produce C triple bond CAg. And this is going to be a white color precipitate. I will use this arrow mark to indicate precipitate, right? So what is this stand for?
Okay.
This is going to be precipitate, right? This is going to be precipitate, and the byproduct will be NH4NO3. NO3 from here, and this released H plus will come and join with this NH4 plus. Yeah, it is very simple. It's nothing is, organic chemistry is very simple, right? So you can simply think, right? So we have C triple bond C. We can have anything here. We can have anything here. Now in the system we have NH3 and AgNO3. So AgNO3 will exist as Ag plus and NO3 minus. NO3 minus, right? So now this is going to be released as H plus, and this H plus will come and join with this NH4 plus to produce NH4 plus, right? NH4 plus, and this Ag will come and combine here, right? So again we have a positive and negative in the system. So here this will make this. Now if the Ag plus combine with this structure, it will produce this, and NH4 plus and NO3 minus will produce this in ammonium nitrate. Is that okay?
Yeah.
Okay. For example, if I write a chemical reaction, it's very simple. How can I write? Now for example, let's say we have CH3 C triple bond CH, right? If you put ammonia AgNO3, ammonia AgNO3, can you predict the yield?
You will have CNO3.
Hmm?
Wait, no, hold on.
CH3.
Give me a sec.
Yeah.
CH3, and then if you add that, it will lose a hydrogen, and then
CH3 C triple bond C, and instead of this one we will have Ag, right? Ag,
Yeah.
and this is going to be white color, right? So now no matter how many R group we have after this C triple bond CH, the ultimately if you have C triple bond CH, now this is kind of thing, right? So in the experiment, for example in the chemistry, in the chemical laboratory, in the chemistry lab, we have to identify which type of functional groups are present, right? Now if you want to test if this type of structure is present, we can simply do it, right? So let's say we have this substrate, this is what we have to identify. Now to identify whether this group is present or not, we can simply put ammonia and AgNO3, and we have to shake, and if we get a white color precipitate, we can conclude that this group is present in the compound. That's all. Very simple, right? And if you don't get a white color precipitate, what can you conclude? This does not exist in the given sample. This is the application of chemistry, not for writing the exam. We are writing the exam just for measuring our understanding, but we have to apply our knowledge in the real world scenario, in the laboratory condition, right? Have you understood this now? Now theoretically we have studied, there is a reagent called Tollens reagent, and it can react with C triple bond CH to produce a white color precipitate. And using this knowledge, we can identify whether, for example, for your experiment or for your research, you need this C triple bond CH, right? And you have you have samples which are not labeled. Then you have to identify them first. So for these purposes only we are going to study. So the first thing we have studied is Tollens reagent. Under Tollens reagent we have studied only one portion. Is that clear now? Do you have any confusions in this regard?
No.
Okay. Now we will move to the second one, right? So again what will be the byproduct? Now why do we call this as acid-base reaction? Because here the release of H plus happens, right? And another one is accepted. So if H plus is removed, then it's going to be acid, and this interaction is between acid and base. So that's why we call this as acid-base reaction. Okay. Is that clear?
Okay. Yeah.
Okay. Now we will move to the second type of reaction related to Tollens reagent. The second one is redox reaction. What's that? The second one is redox. I'm not giving you proper notes. Okay, that's my limitation, right? Because because I don't prepare notes. I just explain everything. Whatever you need, you have to take your screenshots, or you have to take your notes. And I'm explaining everything very clearly in the class itself, so that you don't want to study outside. You can just memorize everything here in the class itself. I'm not giving you the proper notes, because if I want to give you notes, I have to write them down before the class and I have to dictate it, or otherwise I have to make it PDF. I don't have that much of time. That's the problem, right? I don't know
Yeah, okay.
if it is okay, or if you need notes, then I have to take any other measures, right? Yeah. What about you?
Yeah, I think it's fine. I'm just taking screenshots and all most of the time now, or writing it
that's
down.
okay. Okay, that's okay. And I already told you, I think for my students, I always get feedback. Feedback in the sense, at the end of the class, if you could provide a feedback about what you have learned and what you liked or what you don't like or what I have to improve, I can improve myself, right? And I don't remember you sent me a feedback or something. Today you have to submit a feedback about my classes, especially the negative things, so that I can improve them.
Okay.
Okay.
Yeah. Okay.
Okay. Redox, right? Redox. Okay, so when it comes to redox reaction, we should have al group, right? What should we have? We should have al group, al system, right? So we have C double bond O H. We should have C double bond O H. Now here we may have R. This R may be having carbon or hydrogen, anything. It doesn't matter, right? Now here during this redox reaction, the yield will be silver mirror precipitate. Okay. Now, yeah, we can even watch a video, because if you perform this experiment carefully in the laboratory, around the wall of your test tube, you will have the silver mirror deposits. Yeah, can you see? Silver mirror deposit means the silver will deposit on the walls of the what do you call the the experimental flask or a test tube. It will deposit nicely, right? I don't know if you go to your chemistry laboratory and do. I will display some videos also, right? Okay. Silver mirror precipitate, right? So here, if you put this to this solution, ammonia AgNO3, nothing else, ammonia AgNO3, it will produce AgS precipitate. This is going to be our main product. Ag itself will precipitate as a silver mirror. Have you understood that now? But here here the product is different. Here Ag itself will precipitate. If you have al compound, right? Any al, right? Okay. For example, and then the byproduct will be C double bond O. Here we should have O minus NNH4 plus, right? Okay. Because here this is oxidation, right? Here oxidation means I don't know if you studied how to find the oxidation number of these compounds. Okay, we will do this example and then I can explain that. Okay, right. So example CH3 C double bond OH plus NH3 or ammonia AgNO3, right? AgNO3. Now if you have al and if you put tolerance reagent, it will produce Ag. What's the color of Ag? Silver, right? Now you can see here. Now I told you this is redox reaction, right? What's the oxidation number of Ag in the reactant site?
The reactant side, sorry?
What's the oxidation number of Ag in the reactant side?
It will be 1.
Plus 1, right? And here
Plus
it's
one,
going
yeah,
to be
right.
0. So plus 1 to 0. This is going to be reduction, right? So if Ag is reduced, then the carbon should be oxidized, right? So if the carbon oxidized, we will produce CH3, C double bond O minus and NH4 plus. Here, this is oxidized, right? So this is going to be oxidized. We have to find out the oxidation number. Now, can we find out the oxidation number of this carbon?
Of carbon.
So between this carbon and carbon, 0, right? So here
Yeah.
-1 because between comparing carbon and hydrogen, focal NBr ISCPH. So carbon is more electronegative than hydrogen. So it will possess -1. Here it will possess +1. Here this is -2. So, through this, how to find the oxidation number. In general chemistry, did you study this?
Not exactly. Like we didn't learn how to find the oxidation numbers.
Okay. So for example, this is not a big deal, right? This is not a big deal.
Yeah.
For example, okay. So okay. Right. So let's come from the basics, right? Oxidation numbers, right? Anyways,
Yeah.
what can I do? You should have studied this. Okay. Let's keep this for now, and then we can come for oxidation number later if we require more. Yeah, definitely we will require it. Okay, in the next class we will study about oxidation number, right? Now we will study this Tollens reagent. Now, okay, so here from the oxidation number is going to be increased. For carbon, oxidation number is going to be increased, right? So ammonia, nothing else, right? So this is the product, right? Now here, what you should understand is okay. Now we will. We will watch some YouTube videos, right?
Hello?
Yeah. Now
Oh, yeah.
we will watch some YouTube videos related to this Tollens reagent. Okay. So can you see my YouTube screen?
Yeah.
Okay. So aldehyde, right? So this is going to be our silver mirror test, right? So you can watch this video carefully, yeah.
Using Tollens reagent to test for aldehydes. The silver mirror test.
Right. So here the experiment shown in this package may pose. Okay, this is just a disclaimer.
Yeah. Okay.
This video demonstrates how to use Tollens reagent to test for aldehydes. This video first demonstrates the preparation of Tollens reagent. Two tests will then be carried out. One shows a positive result, and the other shows a negative result. Preparation of Tollens reagent. Add 2 ml of 0.3 molar silver nitrate solution into a clean test tube.
So what should you add? 2 milliliter and 0.3 silver nitrate, AgNO3. So silver nitrate means AgNO3 solution, right? Okay.
And then add 1 to 2 drops of 0.3 molar sodium hydroxide solution. Brownish precipitate.
Here they are using NaOH instead of NSC. That doesn't matter because our target group is what? Target group is what? Now I told you to. Now you see ammonia can be sometimes readily available in the laboratory because we need a basic environment. That's why we take NS3. NS3 can be a basic environment. But even it doesn't matter if you take NaOH because our target group is AgNO3. We should have Ag. That is our target. But the environment should be basic. the environment of the experiment should be basic. That's why they are taking NaOH, right? That doesn't matter. Can you understand that?
Yeah.
Precipitate of silver oxide will be formed. Enter 3 molar aqueous ammonia solution drop by drop with a dropper until all the silver oxide precipitate is just dissolved. Do not add excess amount of the ammonia solution. The solution obtained is aqueous diamine silver solution, which is also known as Tollens reagent. Add a small amount of sample to the Tollens reagent.
So first, they have prepared Tollens reagent by mixing ammonia, AgNO3 and NaOH, right? And then they are going to use this reagent for identification.
Shake the mixture gently. And then stack
And you have to shake the mixture. Why? Because in order to increase the reactivity, you have to shake it, right?
it on the bench for 10 minutes. Observe if there is a silver coating formed on the inner surface of the test tube. If there is no observable change, warm the mixture in a warm water bath for 5 minutes.
Okay. Now, sometimes depending on the conditions, we might not get the preferred outcome, right, or preferred observation. In that case, sometimes due to the high activation energy, so we have to reduce the activation energy to increase that, right? So if that doesn't come, if the silver coating is not appearing, then you cannot quickly come to a conclusion there is no aldehyde in the sample. You have to boil it so that you can increase the temperature and reduce the activation energy, right? That's why we are warming, right? So this is kind of practical aspects.
Minutes.
Now you can see after warming it, you can see the silver coating. Can you see the silver coating on the
Oh,
screen?
yeah.
Okay.
If the sample is an aldehyde, a positive test result will be obtained.
So this is a positive result, right? Even after warming, you don't get the silver coating, then that is negative results. So negative results depicts that the aldehyde group is not present in the sample. Yeah?
Okay.
Okay.
If the sample is not an aldehyde, the test will give a negative result. It is important that Tollens reagent should be freshly prepared.
So what is
It is important that
here even after warming you don't get a positive result, which means in the sample you don't have aldehyde, right? You don't have aldehyde.
Okay.
It is important that Tollens reagent should be freshly prepared. Prior to disposal, the reagent must be acidified immediately after use. The addition of acid prevents the formation of explosive silver nitride.
Okay, that's advanced things. Okay. So now have you understood the concept of Tollens reagent?
Yeah.
Okay, so this is for our first thing. Now we will acid base also we will discuss. Tollens test for acid formic acid. The white color precipitate thing. Yeah, you can see, right? So after putting it, you should get the white color precipitate. I hope you can understand, right? And in the laboratory, you can perform all these things.
Okay.
Okay, so we will move to the next one now. Let me share the screen here. Right, so this is our first thing. Now we will go for the Okay, so there are some points you should remember, right? So the first thing is, now for example, let's say I told you if you have C triple bond CH, this will give a positive result with tolerance reagent. But if you have C double bond CH, what will happen? Will it give a positive result?
Yes.
Why?
It has a triple
Technically, double bond or double bond or single bond, this and this, see this, right? So these will not react with tolerance reagent. Right? It will not give any positive result because the acid strength of this and this are comparatively less, right? So
Okay.
first you should know the acid strength. Acid strength is high for C triple bond CH, right? And then C double bond CH, and then C single bond CH. So due to this reason, these two structures or systems will not produce positive results with tolerance reagent. Okay, and then one more thing, there are a lot of things, right? Now you just witnessed an experiment where the system was heated due to negative results, because sometimes the reactivity might be very less. So in order to increase it, we are going to warm it, right? So these things practically you can experience, right? That's all. And then we will move to the second one, right? The second reagent is going to be ammonia CuCl2. Ammonia Cu2Cl2. So this ammonia Cu2Cl2, again similar to the acid base reaction of tolerance reagent. If you have C triple bond CH, if you put ammonia Cu2Cl2, it will produce a red color precipitate. A red color precipitate that will be nothing but C triple bond Cu. This is going to be red color precipitate. But earlier it was white color precipitate, right? Is that okay? Red color or sometimes a reddish brown, right? Depending on the condition, the color might be slightly different, reddish brown, right? And in the different books, they might use different colors. That doesn't matter, right? For example, let's say we have CH3, C triple bond CH, and we put ammonia Cu2Cl2. What will happen? What will happen? We will get a red color precipitate. And what's the structure? CH3, C triple bond C, Cu. This is going to be our red color precipitate. And what will be our byproduct? Now this is again a substituent reaction. So this H releases, again this is an acid base reaction, right? So ammonia and Cl. So NH4Cl will be our byproduct. Similar to the acid base reaction of tolerance reagent. Okay? Is that clear? Okay, now shall we watch a video to demonstrate this also? Ammonia Cu2Cl2. Ammonia Cu2Cl2. Inorganic chemistry. Because if you study only the theory, it's not useful. We have to study with practical experience also.
Rasa batu and Maggi Bubbly Blast
from Nestle.
This is going to be something different. Anyways, you can understand, right? So ultimately you will get a red color precipitate, right? Now we will move to our third topic, that is going to be our feeling solution, right? Give me a sec. Okay, I think we have to stop now, and we will start from feeling solution in next class. When can we
Okay.
have our next class?
My school is starting again, so just normal time Sunday, 10 a.m.
Okay,
Sri Lankan
okay,
time.
okay, that's fine. So we will meet next Sunday at 10 o'clock. Right? Okay.
Yeah, okay.
Right now, if you have any questions, you can ask. Otherwise, we can stop the session.
Yeah. I'll send you the feedback in a bit.
Okay, okay.
Yeah.